Lesson 11-4 Exponential Functions, and in this lesson you learn to graph exponential functions, to determine if a set of data displays exponential behavior, and to solve exponential equations. Why is it important? Because you can use exponential equations to solve problems involving biology and archaeology. So let's take a look at this real-world application in folklore. A wise man asked his ruler to provide rice for feeding his people. Rather than receiving a constant daily supply of rice, the wise man asked the ruler to give him 2 grains of rice for the first square on the chessboard, 4 grains of rice for the second, 8 grains of rice for the third, and 16 grains of rice for the fourth, and so on, doubling the amount of rice with each square on the board. So how many grains of rice will he receive for the last 64th square on the chessboard? Okay, so in this case, we need to create a table and look for a pattern to determine how many grains of rice he received for each square on the chessboard. So here we go. Here's our table. Okay, so for the first square, 2 grains of rice. Pattern is 2 to the first power. Second square, 4 grains of rice, 2 to the second power. Third grace, 8 grains of rice, 2 to the third power. And if we follow that pattern, we basically add uh, 1 to our exponent, okay, with our base of 2. So 2 to the first all the way to the 18th on the 18th chessboard, and on the 36th chessboard is 2 to the 36th power. Okay, and if you notice, by the 30th checkboard, by the 30th chess square, a square on the chessboard, okay, it has surpassed 1,000,000 grains of rice. That's 2 to the 30th power. Okay, so in this case, if we look at the FYI, there are approximately 24,000 grains of rice in a pound of rice. So if you buy a pound of rice, that's just around 24,000 grains of rice. So the wise man was really wise in doing what he did, because at 24,000, that would be between the 14th and the 15th square on the chessboard only. Okay? So notice that when only 36 of the 64 squares are calculated, there are over 68 billion grains of rice right here, 68 billion grains of rice. Okay, how many grains would there be for 64? And we will solve this in exercise 1. Okay, so before we solve this in exercise 1, let's study our pattern. Okay, notice that the exponent number matches the number of square on the chessboard, so we can write the equation to describe y. Okay, the number of grains of rice for a given square x as y equals 2 to the x power. Okay, so this type of function in which the variable is the exponent is called an exponential function. So when your variable is the exponent, okay, look at this one. When the variable is the exponent, it is called an exponential function. So let's define an exponential function. An exponential function is a function that can be described by the equation of the form y equals a to the x, where a is greater than 0 and x is not equal, and a is not equal to 1. Okay, if you notice, if a is equal to 1, what's going to happen is that doesn't matter how much you raise it by, it's still going to be equal to 1. Okay, so let's after defining our exponential function, we can move on to another concept in this section. Okay, and you can do this too. If you fold a large rectangular piece of paper in half, unfold it and record how many sections are formed by the creases, and refold the paper. So this is a modeling of an exponential function, and this is just getting, let's say, get an 8.5 by 11 piece of paper. Okay, white piece of paper will do. Fold it in half. Okay, unfold it and record how many sections are formed. So if you fold it in half, you have two sections, and then reform the paper. Or sorry, refold the paper. I will put a new twist in this problem. Instead of folding it and recording the number of sections there are, let's see how thick a paper will be if you fold it, let's say around 40 times. And this video will show you a very interesting fact. Okay?
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1,000th of a centimeter in thickness. That is 10 to the power minus 3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of a newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2,000ths of a centimeter in thickness. If we fold it in half once again, the paper will become 4,000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1,024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if you fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
So that was a good introduction to exponential growth, and that's exactly what we have here in folding a piece of paper. If you continue to fold a piece of paper half, what happens is that the first fold will give it 2, the second fold will give it 4, so it doubles just like the rice. Okay, so continue folding it in half and recording the number of sections until you can no longer fold the paper. So how many folds can you make on this one? It's about probably 6. Okay. And if you do that, how many sections were formed when you fold it 6 times? It'll be around 64. Okay, so what exponential growth is modeled by the folds and the section created? Again, just like the rice, it's going to be y equals 2 to the x power, just like the one that we saw on the video. Okay, It's interesting how a piece of paper can reach you to the moon. Okay? So as with other functions, you can use ordered pairs to graph an exponential function. Use a table of values in a calculator to find ordered pairs that satisfy y equals 2 to the x power. While the negative values of x have no meaning in the Rice problem, they should be included in the graph of the function. Connect the points to form a smooth curve. So if we create a table of values such as this one, when x is equal to -5 using a calculator, end up with 0.03125, and then go all the way down to 4 when x is equal to 4, y is equal to 16, and when x is equal to 0, y is equal to 1. Now, what do you notice about when x is equal to 0? This is our y-intercept. Okay? So our y-intercept would be 0, 1. And if I graph that, okay, we graph that particular table of values from our exponential function, this is what we're going to have. Okay? So you will have a graph that slowly slants upward really fast. Okay, so it slants, the slope, well, it's a contradiction, slowly slants upward really fast. But the growth or the increase, okay, in the graph is basically a very steep. Okay, so the slope becomes steeper and steeper, and this is what we call an exponential function. And if you notice, that's our y-intercept, 0, 1. Okay, and if you also notice, as you go less than -5, -6, -7, and so on and so forth, your y will become smaller and smaller and smaller, but at the same time, it will never reach 0. Okay? So, let's take a look at this graph. Notice that the graph has a y-intercept of 1. Does it have an x-intercept? Okay, well, we just answered that question. Since it will never reach 0, okay, you will not have an x-intercept for this particular graph, but we'll verify that in example 2. So the graph shown above represents all real values of x and their corresponding values for y for y equals 2 to the x power. So you can also use a scientific calculator to help you find ordered pairs to graph the exponential functions. For example, y is equal to 3 to the x power and x equals -2. So all you need to do is get your scientific calculator and press 3 and press the button y to the x power and then press number 2 plus or minus the equal sign, and that's what you're going to get. So 3 raised to the -2 is 0.1111111. Okay? So let's take a look at example number 1. Graph each function, state the y-intercept of each graph. So you have y equals 3x, and remember, in order to find your y-intercept, okay, x should be equal to 0. So in this case, okay, y is equal to 3 to the 0 power, and anything raised to the 0 power is 1, so y equals 1. So when x is equal to 0, y is equal to 1. Our x-intercept would be 0, 1. And let's take a look at our table of values, and here you will see, okay, that this is our y-intercept. And these are all random values for x, and these are the values for y given the values for x. Okay, and if you graph this, this is how it's going to look like. Okay, y equals 3 to the x power, and the y-intercept is 1. Okay, now if you notice again, it slowly decreases as you as you find values less than 3. The y will slowly decrease, but will never, okay, pass the uh, x-axis. Okay, it will come closer and closer to the x-axis, but it will not it will not cross the x-axis. Okay, so let's take a look at b. Y equals 1/3 raised to the x power. So 1/3 raised to the x power, again, we want to find the y-intercept. Okay, and the y-intercept is when x is equal to 0. So y is equal to 1/3 raised to the 0 power. Okay, and again, our y-intercept would be 1. Okay, putting that in tabular values, there's our y-intercept, 0 equals 1. And again, okay, look what happens to our exponential function, the graph of our exponential function. Okay, here, okay, your base is a whole number. Okay, it's an integer. Okay, in case of 3, and the graph slopes this way. In letter B, your base is a fraction. Okay, less than 1. And if you notice, the slope, okay, the shape of our graph is a little bit different from the A in such a way that it is almost the opposite of A. Okay, so you have your exponential function y equals c to the x power, which looks like this, and your exponential function y equals 1/3 raised to the x power, which looks the opposite of letter A. Okay, let's take a look at letter C, another scenario. Y equals 3 to the x minus 7. Now we have a constant, okay, which is -7. And let's see how this is going to look like. First, we need to find our y-intercept. Again, our y-intercept is when x is equal to 0. So this is y equals 3 to the 0 power minus 7, or y equals 1 minus 7. Okay, so 1 minus 7 is -6. Our y-intercept would be -6. Ordered pair would be 0 and -6. And if we put it to our table of values again, and using our scientific calculator, this will be our table of values for our exponential function y equals 3 to the x minus 7. Okay, and that's our y-intercept. And if we graph this, this is how it looks like. Now you notice that this one now crosses the x-axis, but comes very close to -7. Okay, so the line slopes down all the way very close to -7, but will never cross -7. Okay, so what do we notice here? Here, our constant is 0, and that's why it slopes down, but it will never cross 0. Same thing with letter A. Our constant is 0. It slopes down, okay, and it goes smaller and smaller, very close to 0, but will never be equal to 0. In letter C, however, our constant is -7. So therefore, with -7 being our constant, our exponential graph now goes down and goes very close to 7, but never passes 7. So if I find values of x that are less than 3, okay, it will go closer and closer to -7, but it will never be actually equal to 7. Okay? I hope that makes sense. If not, rewind the video. So, how do you know if a set of data is exponential? Okay, one method is to observe the shape of the graph. Okay, but the graph of an exponential function may resemble part of a graph of a quadratic function. So that's one method. Look at the graph. Okay, another method, okay, is to look for a pattern in the data. So method 2 is looking for a pattern in the data, and that's how you find out if it's an exponential function. Now let's take a look at the example 2 and see how this works. To determine whether each set of data displays exponential behavior, method 1, okay, is look for a pattern. Okay, and in this case, the domain values are at regular intervals 0, 5, 10, 15, 20, 25. Okay, let's see if there is a common factor among the range values. Okay, and if you look at our range values, 800 times 1/2, there is a common factor of 1/2. Okay, and since The domain values are at regular intervals and the range values have a common factor. The data are probably exponential. So the equation for the data probably involves 1/2 raised to the x power. So again, this is considered to be an exponential function because your domain values are at regular intervals and you have a common factor for your range values. Okay? And if we use method 2, which is graphing the data, you'll end up with this graph. And this graph shows a rapidly decreasing value of y as x increases. Okay, so this is a characteristic of exponential behavior. Okay, and that's how we figure out if it displays exponential behavior or not. Let's take a look at letter B and see how this works for this example. You have 0, 5, 10, 15, 20, and 25. Again, method 1 is looking for a pattern. Look at our domain values. The domain values are regular intervals of 5, 0, 5, 10, 15, 20, 25. No problem there. Okay. The range values have a common difference of 3, but they do not have a common factor. So they have a common difference of 3. Okay. That means if they do not have a common factor, even though the domain values are at regular intervals, this data do not display exponential behavior, but rather a linear behavior. Because if you look at the method 2, and if you graph the data, this is how the graph would look like. It's a straight line. Okay, so this is the graph of a line, not an exponential function. Okay, let's take a look at the next concept that we need to understand. Exponential functions are often used to describe real-life situations. In the late 1890s, Henry Becquerel discovered that fossils contain naturally occurring radioactive atoms of carbon-14. When an organism is alive, it absorbs carbon-14 from the sun. So, when the organism dies, no more carbon-14 is absorbed, and the initial amount of carbon-14 begins to decay gradually into other elements. Okay, so the half-life of a radioactive element is defined as the time that it takes for 1/2 of the quantity of an element to decay. Again, let me read that because it's going to be confusing. The half-life of a radioactive element is defined as the time it takes for 1/2 of the quantity of the element to decay. And we'll look at the table. So radioactive carbon-14 has a half-life of 5,730 years. This means that after 5,730 years, half of the original amount of carbon-14 has decayed. Okay? So in another 5,730 years, half of the remaining half will decay, and so on and so forth. So you'll have 1/4 left. So this pattern of decay can be described by the exponential function a equals 0.5 t. 0.5 obviously represents 1/2, where a is the decay factor and t is the number of half-lives. So let's take a look at the chart to see how 64 grams of carbon-14 decays over several half-lives. Notice this relationship to the exponential function a equals 0.5 t. So 0 half-life at 64 grams of carbon-14, you have 64 times 0.5 to the 0 power, or simply 64. 1 half-life, you have 32 grams left. Remember, 1 half-life is 5,730 years. So after 5,730 years, your original 14 grams of carbon-14 is now 32 grams. After another 5,730 years, your original 32 grams, your 32 grams now becomes 16 grams because 64 times 0.52, and so on and so forth. After the 9th half-life, okay, you'll have 0.125 of a gram left, okay, because it is 64 times 0.5 raised to the 9th power. Okay, so this is a good indication of how to guess, not guess, but estimate the age of a particular fossil by just finding out the amount of carbon 14 left in that particular fossil. Okay? So if the initial concentration of carbon 14 in a living organism was 256 grams in example 3, determine the concentration of carbon 14 remaining in a fossil for each situation. Let's say the organism lived 1,000 years ago, okay, and the organism lived 10,000 years ago. So let's answer letter A. The organism lived 1,000 years ago. So the first, determine how many carbon 14 half-lives there are in 1,000 years. Okay, so we get 1,000 and we divide that by 5,730. So there are approximately 0.1745 half-lives in 1,000 years. And then after that, we determine the value of the disintegration factor when t equals 0.1745. So that means we use our formula, A equals 0.5t, okay, and we raise 0.5 to 0.1745. And using a calculator, A equals approximately 0.886, okay? And after getting 0.886, we simply multiply the original amount of carbon 14 by this factor. So you get 256 grams multiplied by our disintegration factor of 0.886 will give us 226.8 grams. Okay? So in this case, okay, uh, the concentration of carbon 14 remaining in a fossil uh, that lived 1,000 years ago is 226.8 grams. Okay? In letter B, okay, let's do 10,000 years. First, find how many half-lives there are in 10,000 years, and then we get 10,000 divided by 5,730, approximately 1.75 half-lives, and then determine the value of the disintegration factor when t equals 1.75, okay, and we use our formula again, A equals 0.5 raised to 1.75. Using a calculator, it'll be 0.297, and then we get that number and again multiply it by 256. We end up with 76 grams. Okay, so after 10,000 years, okay, the organism lived 10,000 years ago, it would have 76 grams of carbon 14 remaining. Okay? And you can also use algebra to solve equations involving exponential functions by using the following rule. And this rule, okay, if you knew this earlier, you would have probably answered the bonus question on the chapter 9 test. Okay, and that's the reason why it was a bonus question, because you had to figure that out without knowing this rule. And this is the rule. Suppose a is a positive number other than 1, then if you have a raised to the x sub 1 equal a raised to the x sub 2 if and only if x sub 1 is equal to x sub 2. Meaning, okay, if they have the same base, you can simply take out the base and know that x sub 1 is equal to x sub 2. And let's see how this particular property is applied in example 4. Okay, and the skills you learned when solving quadratic equations can be helpful when solving some exponential equations. You have 63 to the third equals 4x squared. Now again, they do not seem to have the same base, but actually they do, and let's see how. So the two quantities do not have the same base or value for a. However, 64 is a power of 4. Okay, so in order to use the property of equality, we must rewrite the terms so that they have the same base. Then we can use the property of equality for exponential functions. So we start with 64 raised to the third power equals 4x squared. And then we know that 64 is a power of 4. We can write 64 as 4 cubed raised to the third power. Okay, so 64 is actually 4 cubed, and we simply brought down the third power. Okay, so now we have 4 to the ninth, okay, rules of exponents, okay, equals 4x squared. And now that they have the same base, we simply equate 9 equals x squared. So property of equality for exponential functions. And then we subtract 9 to both sides. Now subtracting 9 to both sides, realizing that x squared minus 9 is a difference of squares. So we have x plus 3 times x minus 3 equals 0. Okay, and using the zero product property, we have x plus 3 equals 0 and x minus 3 equals 0. We find the values for x as negative 3 and 3. Okay, and if we check our answer and substitute it to the original equation, okay, 64 cubed equals 4x squared, and substituting the value of negative 3, okay, sorry, 3 for now, and then we'll do a negative 3 on the other side. So 64 cubed, is it equal to 4 cubed raised to the second power, okay, or is it equal to 4 to the ninth power? 64 cubed is 262,144, and 4 to the ninth is the same number. Using negative 3, okay, we end up with the same answer. Therefore, solutions 3 and negative 3 are correct. Okay? And the secret word for this particular lesson is paper. Secret word is paper. Okay? Thank you for watching.